Okay, in this video, we're going to look at the kinematics equations and see which ones are appropriate to use in certain instances. That's really kind of the hardest part about this, is you have a whole bunch of equations, but you need to figure out which one to use. So sometimes that can be a little tricky. So our first equation, okay, you had it right in 6th grade. Remember, distance equals rate times time? Okay, that works. That works. You can use this when you have no acceleration, or if you know the average velocity. Okay, this rate here is your average velocity. So sometimes we will use distance equals rate times time, and sometimes it will be that easy. Okay, but this is when there's no acceleration, or if you do have an acceleration, you do know the average velocity. So sometimes this is the easy way to solve things. But the other three that we're going to use are the position, remember x is position, 1/2, ooh, this one's ugly, at squared plus v initial t plus your initial position. Okay, so most of the time, you guys, most of the time this initial position is going to be 0. So most of the time you're going to start at 0. So most of the time you're not going to use that. Every once in a while you will. So I leave it in there as part of the equation. Every once in a while it'll be there, but most of the time it is not. So that's one equation. The other is your final velocity is equal to the acceleration times time plus your initial velocity. Now, do you notice that I'm making my t's with hooks on them? Okay, I'm making my t's like this. Why do you think I might be doing that? Okay, look at a t and look at a plus sign. If you look at a plus sign, look really closely, and you've got a t here next to a plus sign, a lot of times you're going to get those mixed up. So I really encourage you to make your t's with hooks on them so that you can tell, hey, that's a t, not a plus sign. And the last one, which is actually very handy. This one, if you don't know the time and you don't want to find it because you would use it in the first instance, and if you look at the first instance, ooh, yuck, that's a quadratic equation. Yes, this is a quadratic equation too, but it's usually easier to solve. V final squared equals V initial squared plus 2ax. Okay, so our final velocity squared is equal to our initial velocity squared plus 2 times the acceleration times, now this x is your displacement. Alright, so pause the video, write these guys down, because you're going to be using these a lot. Okay, this is a partial list of implied information for your kinematics equations. In the problems, they're word problems. Okay, I'm sorry, they're word problems. So you have to be able to pull the information out of the word problems. So some information that's kind of implied. If something starts from rest, that means it was resting in place. And so its initial velocity is 0. Okay? If it comes to a stop, hey, how fast are you going when you stopped? Hey, you're going 0 again. So your final velocity is 0. Now, if you're going at constant speed means that your speed isn't changing. So if your speed isn't changing, your change in velocity is 0. So if your change in velocity is 0, then your acceleration is 0. So constant speed, that's when you can use that distance equals rate times time equation. That's often handy. And then if something's dropped, when it first leaves your hand and you drop it, its initial velocity is 0. Now, there's another piece of information. Its acceleration, gravity's going to pull it down, and it's going to speed up every time it falls. We're going to talk more about free fall and throwing things up and down in a later video. but just get you started, the acceleration due to gravity is 9.8 meters per second squared. So whenever gravity makes anything go down, because gravity only works down, so gravity is always in the down direction, the acceleration due to gravity is 9.8 meters per second squared. So if something's dropped, then gravity's pulling on it. You know, I drop my ball and hey, my ball falls. Why does it fall? Oh, because gravity's pulling on it. So the Earth's gravity is going to cause it to accelerate at 9.8 meters per second squared. So that's just to get you started there. Okay, so here's a few problems from your pretest that have different situations so that we know how to solve these and how to figure out which of those 4 equations we have. Because remember, we have the distance equals rate times time and then the other 3 that have acceleration in them. So here we have Anne driving down a street at 60 kilometers per hour. Suddenly, a child runs into the street. Oh no! It takes Anne 0.78 seconds to react and apply the brakes. How far will she have moved before she begins to slow down? So, we know Anne is still going at 60 kilometers per hour. She's still going at 60 kilometers per hour, so she's going at constant speed. So constant speed, or she's not speeding up, she's not slowing down, that's a big hint that we can use distance equals rate times time, which is going to make our life really, really, really easy. Okay, now we have an issue here. Do you see our speed? Pay attention to these things. See your speeds in kilometers per hour? You need to convert that to meters per second. Referring to your previous video, remember you did derived units, so see if you can pause the video and see if you can change your 60 kilometers per hour to meters per second. Okay, you paused the video, right? Did you come up with 16.67 meters per second? If you didn't, this is how I got it. So follow this process. Change my kilometers to meters. And then I know 1 hour is 60 minutes and 1 minute is 60 seconds. Or I could have just said that 1 hour is 3,600 seconds. Because remember, that was something we wrote down also. Okay, so distance equals rate times time. Our distance is equal to our rate. And we're going to use the 16.67 meters per second. Times our time, 0.78 seconds. Okay, and see how the seconds cancel out? And so when we multiply that, we get 13 meters. Okay, 13 meters. So think of 13 meter sticks end to end. That's longer than the classroom. That's even before she can start to apply her brakes and stop. So you can see how difficult it might be to stop when you're going 60 kilometers per hour, which is really only about 45 miles per hour. Okay, here we go again. A particle moves according to the equation x equals 10 meters per second squared times 10 times squared, where x is in meters and t is in seconds. This again is number 22 and 23 from your pretest. Find the average velocity for the time interval from 2 to 3.16 seconds. So we have that average velocity in there. So that tells us again that we can use distance equals rate times time. Okay? Distance equals rate times time. That rate is either your average velocity or your constant speed. So what we need to do is figure out how far do they travel from this 2.02 seconds to the 3.16 seconds. That's what we need to do. So the equation tells us distance and time. So really all we have to do is plug those times in there to find out what kind of distances we're talking about. So for the first time, we have x equals 10 times 2.02 squared. Okay? Because all I did was put the 2.02 in for time. And that'll come out to 40.8 meters. Okay? Now let's try you go ahead and try the 3.16 and we'll compare answers. So pause the video, you try the 3.16. Did you get 99.9 meters? Okay, so how far did he go during that time interval? He went from 40.8 meters to 99.9 meters. So if we take the difference between those two, we find out that he traveled. So the distance he traveled, that's going to go in for distance, is 59 meters. It's pretty much 59, 59.056, close enough. And that's going to equal our rate, which is what we're solving for. Now, how long did it take him to do that? What are we going to do? Find the difference between our two times. And that comes out to 1.14 seconds. So it's our total distance, remember we did this before, divided by our total time. And so we're going to get that our rate is divided by 1.14, 51.8 meters per second. He is flying. Okay? 51.8 meters per second. All right. Part 2 of 2, same thing. So you try to do that, and I'll put the answer up from the pretest. I hope you paused the video and tried to work it out yourself, but you should have gotten 41 meters per second. In 2.12 seconds, he's gone 44.9 meters. That makes our total distance traveled 4.1 meters in that 0.1 seconds. So you get 41 meters per second. Okay, so those two are constant speed. The next one has acceleration. All right, this is skipping way down in the pretest. Now, here's how you solve these problems. When you have acceleration, we basically have 5 variables. We have x, let's write them down. We have x, we have v initial, we have v final, we have our acceleration, and we have our time. Okay, remember x is our distance, our initial velocity, our final velocity, our acceleration, and our time. So if you list these 5 variables down, okay, and we want to know what acceleration, so that's what we're looking for. It says it has to have a liftoff speed of approximately 125 kilometers per hour. So that means when the plane takes off at the end of the runway, it needs to be going 125 kilometers per hour. Now, what do we have to do to that? Do you remember? Pay attention. Kilometers per hour. So what do we have to do that? Did you work it out? I hope so, because you should have gotten 34 meters per second, 34.7 meters per second. So let's think about what other implied information might be in here. The aircraft has a liftoff speed of that, constant acceleration if it's going to be airborne after a takeoff run of 251 meters. So our displacement is that 251 meters. What do you think the plane's initial velocity is? Right, 0 meters per second, because the plane's going to start at rest and it's going to go speed up. So we are looking then for acceleration. So we're going to look at our kinematics equations, and we want the one that doesn't have time in it. You looking? Right. So we want the equation v final squared is equal to v initial squared plus 2ax. Okay, our final, we're going to use the meter per second version of it. 34.7 squared is equal to our initial, 0 squared, plus 2, we're looking for our acceleration, times our displacement, 251 meters. Okay, so let's do that math. And then pause the video, do the math, and let's check our answer. You should have an acceleration of 2.40 meters per second squared. Good? So
Check. We're done with that first one. Let's look at the second one. Part 2 says, what's the corresponding takeoff time? So we have the same givens everywhere. We want to know what the time is. So here's kind of a cool thing, is at this point, there's two different ways we could solve our problem. One way we could solve our problem, because we have two different equations that have time in it, we could go V final equals V initial plus acceleration times time. Or we could use x equals 1/2 at squared plus v initial t. We're looking for time. Which one of these equations looks like it might be easier to use? Generally, this one's going to be our easier equation to use. This time, though, this equation will work just as well, because what's our initial velocity? 0. So if our initial velocity is 0, if we stick 0 in here for our initial velocity, what happens to that whole term? It drops out, because 0 times anything is 0. So this works out to 1/2 at squared. So either way, it's not that bad. So let's do it both ways. So our final velocity, 34.7, is equal to, this is 0 too, so that drops off. Our acceleration, 2.4 t. So here we get t equals 14.4 seconds. Now, in a perfect world, we will get the same answer using the other question. And physics happens to be one of those perfect worlds. So, what's our displacement? 251 is equal to 1/2. We know our acceleration, we just found that. That's the 2.4 t squared. So solving for t here, you should get 14.4 again. Double check, pause, try it. Yep, 14.46, which is 14.4 seconds. So we get the same time no matter which way we solve it. So again, there are many ways to solve a physics problem. There is not just one way to solve a physics problem, and that's one of the things that's very, very, very important about doing these problems, is that there is more than one road to Rome. All roads lead to Rome, though. Okay. Now the last part of our problem says, if the aircraft accelerates at this rate, what speed will it reach 10.7 seconds after it begins to roll? Okay, so after it begins to roll. So that means it still has an initial velocity of 0. So we're still working basically the same problem with the same knowns and unknowns we were working before. So the difference is our time. So let's just relist our variables. We have x equals 251 meters. We know our initial velocity is 0. We have a new final velocity, because that's actually what we're looking for. What speed will it reach in 10.7 seconds? So our time is the 10.7 seconds. And it's the same plane, so it's accelerating at the same rate, 2.4 meters per second squared. Actually, our displacement is not going to be that 251 meters, because at the end of 10.7 seconds, it is not going to be in the same place. So for that right there, we want to cross that out. So we don't want the 251 meters. We don't know the displacement. So we need an equation that doesn't have displacement in it. So when we look at our three equations, we find out that if we have V final equals V initial plus AT, that one doesn't have displacement in it. The other two do. One has 2AX in it, and one says X equals. So we need an equation that doesn't have displacement in it. So our final velocity is equal to, remember this is 0, so that drops out, 2.4 times 10.7. The final is equal to 2.4 times 10.7 is 25.68 or 25.7 meters per second. And that will give us a pretty good idea of how to solve those problems. So we can see that the real trick to doing these is you want to look for the equation that doesn't have the variable that you don't want. Okay, so you want to look for the equation that doesn't have the missing variable. But does contain your known and your unknown. So the trick is just finding the right equation. And if you list your variables, then it's a lot easier to find that right equation. All right, I'll see you tomorrow. Keep thinking. Bye-bye.